Hello, everybody. It's 10 a.m. in Colorado. It's time for the seminar. Welcome to the 2022 Econ Seminar Series. And it's an honor and a pleasure for me today to introduce Dr. Gabriela Adler. Gabriela is Chief Scientist Officer at BreezoMeter. She completed her undergraduate students in aerospace engineering at the Technion, Israel, and conducted her master's and PhD at the Weizmann Institute in Israel in the field of atmospheric science. Her master's research focused on emission from diesel car exhaust, and her PhD focused on key characteristics of process aerosol in the atmosphere. After her PhD, Gabriela continued her research, working as a scientist at NOAA in Boulder, where she conducted atmospheric measurements related to fire emissions and carried out aircraft instrument development. Today, she will tell us how BreezoMeter combines small sensor, dispersion models, satellite information, machine learning algorithms, and more to provide easy-to-use, actionable data for companies and individuals. Before starting, I want to remind you that you can type your question at any time during the talk in Slido in the space below the window where the video is playing. The questions will be read at the end of the seminar. And with that, I introduce you to Dr. Adler. Gabi, please take it away.
Thanks for the invitation and thank you for the introduction. So I want to first of all say that I'm really excited to talk in front of this audience, both because I have a warm place in my heart for Boulder. I lived there for almost 4 years while working at NOAA, and I really like this place. And also, I think this talk is kind of, I'm going to talk about BreezoMeter, but I think my personal journey is kind of summarizing the title, which is bridging the gap between the academic world and the industry. So I moved from the scientific world or from the academic side to a startup company. And my motivation was that I wanted to bring to people this knowledge that is in the academic world. I wanted them to be able to use it, to take actions, to see the information. So it all relies on the shoulders of giants, like the work that you guys are doing. And I'll tell you a little bit about the company, and then some motivation or some introduction, short one, to air pollution or air quality. And then a little bit about what's available in the different EPAs around the world and in the academic world, and what is requested by people, what is requested by the different companies, and how the company that I work in, BreezoMeter, is bridging this gap between the academic world and what people want, and what is our solution, how do we do everything we do. But first, just a few words about what is BreezoMeter. So we are a startup company, 8-year-old startup company, so quite old. And we have around 100 employees. We're growing rapidly. So by the end of this year, we'll probably have around 160. That's a plan. We're a big data company that has a multidisciplinary team. So we have data scientists, machine learning experts, environmental engineers, UI, UX developers, backend developers, and really it's scientists. It's a really unique, I think, environment in the sense that we combine different expertise together to bring environmental information to the public and to companies. Currently, we provide air quality or air pollution, pollen data, fire polygons, and also we provide weather, but this is not our product. It's something that we purchased from another company as a one-stop shop, and you will understand why during my talk. My work, I'm the chief scientist in the last 3 years. and I also lead the science team in BreezoMeter. We're currently 7 scientists, and some of them atmospheric scientists, some of them medical data researchers, and each scientist in the group is responsible for a different vertical. So this is something I'm not going to talk about in this talk, more about air quality, but if you're interested in other things that we do, I'm happy to talk about it later after. So our mission is to improve the health and safety of billions of people worldwide by reducing their exposure to environmental hazards. And we do it by health-focused environmental intelligence and insights. So I don't think I need the motivation for this audience, but it's always good to repeat. Why should we care about air quality? So this is what I'm going to talk about, this product of air quality during this talk. So 7.1 million deaths are associated worldwide annually, are associated to air quality and premature death. And the problem is that it's an invisible challenge. So something that we cannot see, we cannot feel, we cannot smell. Sometimes we can, but most of the time we can't. I think ozone is a really good example for that, and that there are many occasions of the beautiful day effect of everything is great and nice, and there is high ozone and people are just not aware of it. And imagine if you could put on glasses that you can see the pollution that you have around you, and more than that, the exposure that you inhaled during your day or during the last year or during the last 20 years. So this is the challenge. And air quality in terms of health, it affects, first of all, it affects all of us, of course, but it affects us differently depending on the segment of the population. So pregnant women and kids and older or senior citizens are exposed to their different way of experiencing air quality, and their symptoms are very different. And there are also short-term effects, that this is mostly what the governments are reporting, or different governments around the world. I didn't say it in the beginning. We are providing information in over 100 countries worldwide. I'll talk about the resolution and everything later, but to us it's a global challenge. So the different governments usually report air quality in terms of the short-term exposure, which the results is mainly for people that are sensitive groups like COPD or asthma patients, and they feel it immediately, like headaches and coughing and skin irritation and so on, but it affects basically all of us. We all feel these symptoms in very high concentrations. And the long-term effects, which air quality or air pollution basically affects every organ in the body, really every organ. Starting from the brain, there are papers or research that shows that it causes dementia and cardiovascular diseases and liver, and of course lung diseases like COPD and asthma. This is the most straightforward, I think. And then there is also impact on fertility for both men and women. I also read one paper that said it affects happiness, which I'm not sure it's true, but this there is one paper at least. And so what's available by the government data platform? So this is an example from AirNow that we actually work with, the US EPA AirNow. And they're, I think, a very good example compared to other countries in terms of they provide to people a much more intuitive information compared to other countries. So what do we see here? We see the different governmental stations and the current air quality. This is of course not current, it's a photo that I took, but the current air quality in Boulder, you can see that the stations are quite far from each other, and you have one number. And this number in the case of air now is based on only PM 2.5 and PM 10 and ozone. So not all pollutants. And another example is from the European Environmental Agency. This is Spain. You can see the different colors. It's the same idea. It's the air quality index. So the air quality at this hour, and you can see the stations are very far from each other. And also there are many stations that are not active, the ones that are kind of grayish. But there are other examples also from other countries that don't even show maps and so what could interest the public in terms of air quality? So I gathered here some of the questions that we get to our website or to our app, but there are many more that I'm sure you ask yourself or you heard people ask you. So where should I buy my house? So this is more for long-term air quality. People want to know, for example, if they have a relative that is has in a sensitive group, like an asthma patient, they want to know where should they buy their house and where should they raise their kids. And this is something that if I look, for example, at the map of the air quality index of the European Environmental Agency, I don't get this information. It's long-term air quality information or long-term exposure, historical data that is usually not available. In addition to that, it's very, very hyper-local. So I want to know where to buy my house in which street also. And I want to do the statistics for my street and not for another street. And you can see that the stations are very, very far from each other. And it's very not hyper-local. The other example of hyper-local information that is more real-timey is which playground should I take my kids? I want to know if I'm inside Boulder. I want to know if to go to one I forgot the names of the playground, sorry, one or the other, and you can see that the information from the government monitoring stations are not in every playground, and so I have the same information basically for the entire region. So it doesn't help me. Should I pack my allergy medications for the next vacation? So people want to know not only about air quality, they want a one-stop shop, something that I mentioned before. They want to know not only how the pollution affects them, but also their allergies. And if they travel from one location to the next, it can be from different countries, it can be within the US. If this place is now they have a high pollen or high specific tree pollen season, and if it's high today or tomorrow as well. And also we know that air quality or air pollution is enhancing the symptoms of people that suffer from allergies. And hence they want to know the combination of these things as well. So this is one example of this one-stop shop. And what time should I run? So what time should I run? It's a matter of how frequently, so hyper-local, but also how frequently is the information updated. So for example, in France, there is a delay of 4 hours between the reporting of the government monitoring stations and by the time it reaches the public. And that's too late because air quality, as you know, changes several times a day. So it doesn't help people answer these questions. And there are many more other use cases, just an example. So what could interest on the other hand? So I talked about the people and said our goal is to help people. But what could interest companies? So there are different use cases and there are different companies that are interested in air quality data or air pollution. One example is smart buildings. So I have a slide about that. Yeah. So smart buildings, but also HVAC and any air purification. What they want to know what is the air quality outside to compare to, usually they have sensors inside the house, either on the air purifier or other location in the house. And they want to inform people when to close the windows and operate the air purifier or automatically operate it, or the other way around, when should you open the windows and close it. They want to do it from their reasons because it makes it more usable for the companies that actually sell these products, because otherwise you put the air purifier somewhere in the storage and you don't use it. And it's good also for people because you save electricity and you basically protect yourself around the clock. So another use case is healthcare. So different healthcare companies, they provide, there is, now it's, especially with the COVID, we see a trend of going to personalized information. So many health providers, healthcare companies, pharmaceutical companies have different apps to help and manage some of the patient's symptoms. So one use case could be, for example, is to show them what are the levels of different trees in terms of pollen that they can show to the users, and they can see if they're sensitive to that, or the other way around, they know they're sensitive to that and they can protect themselves. Same thing with companies that are skin companies, for example, is something that I discovered only when starting to work at BreezoMeter, that there is a connection between, or correlation between air quality or air pollution and your skin. It creates exposure, long-term exposure to air quality creates wrinkles and spots. And so different skin companies are also interested in that. Mobility. So we have a nice visualization. So different car companies or automotive companies, they want to know what is the cleanest route to choose to drive in. Again, this is something that I'm sure you haven't encountered because it's still in their innovation and not yet out in the market. But this is one use case. And the other, some of the automotive companies, they have an air purifier inside the car, so they want to know when to operate it. Another use case or interest from cities and authorities, so they want to do traffic navigation and city management. Another use case is advertising. Again, for example, pharma companies, they want to know where to advertise different medications. And fitness. So fitness, we see different companies that do, for example, the cleanest route for trails or asthma related apps, etc. So what I try to kind of, for this talk, I try to summarize how I see it, at least, in what's important for both general public and companies, and what's basically the problem in the information that exists right now. So one thing is all of us, the people and companies, we want information that is easy for everyone to understand and take actions. People tell us 500 ppb doesn't mean anything for me, right? And I'm not talking to you, but generally to the people on the street. And they want to know, what does it mean for them? What's the effect for them? How does it affect my health? And this information is available through the air quality index that is in different countries. However, it has many issues because the air quality index, as I showed before, for example, in air now, is based only on 3 pollutants, right? Or even 2, if I take PM as 1 pollutant. And different countries have different air quality index. So it's not comparable. I'll show you an example. This is the air quality index of the US, of the US EPA versus India. So you can see that for PM2.5, for the same exposure, it's 24-hour exposure of PM2.5, the translation to the air quality is very, very different, right? You can see that from 0 to 30, it's considered to be good, where in the US, it's considered to be moderate. And there are even more extreme examples. And I gave here an example from our map. So we're providing all the air quality indices around the world, but also we have our own air quality index. And I compared here the same time and location for different indexes in China. So BreezoMeter and China, and you can see very different results. One of them shows low and the other shows good air quality. And it's the same exact concentration and the same exact duration. So people want to know how it affects them. They want it to be based on health implications and not on other parameters like politics. They want it to have a global solution, both in terms of the data. If I'm a company that wants to provide data in the entire world, I want to have global data, so not to collect data from different sources, like different EPAs around the world. And I also want it to be comparable from one place to another. I want to be able, as a person, I want to be able to compare Shanghai to New York easily in terms of the air quality. And the solution should supposed to be global, but also very local, because I'm interested in this park or that park, right? I said before. The data should be available all the time, 24/7 with no downtimes. And this is something that currently is not the case in different monitoring stations. It should have a high spatial resolution, meaning very dense grid. It should have a high temporal resolution, so updated once an hour or more. Easy to use and integrate. So usually companies ask for a very simple code. In our case, we provide an API code that is very easy to just take and integrate into any system. The data, as I said before, should be calculated for different air quality indexes. If I live in Germany, I'm used to looking at the information in the German air quality index. So I want to be able to have that as well, in addition to the other things that I mentioned before. And all environmental data should be given together. So one-stop shop. I gave the example of the allergy, but I can give another example of asthma. If I'm an asthma patient, I want to be able to know how it affects me. And what affects me is relative humidity, its temperature, its ozone, its PM. They have different exposure times that affect me, and also pollen. So I want to be able to integrate all of these things together to understand how it affects me. And I want to see this as an insight if I'm an asthma patient, but also for different companies, like the cleanest route. If I'm an automotive company, I want this to be a code that calculates what is the cleanest route. So skip this. So what do we do? We provide a map you can see here, this is our website. So this is how it looks like. You can look at it later with the air quality index that of BreezoMeter. So you can compare different location, different works, but you can also switch to different air quality index. If you want to look at Germany, or you want to look at France or the US, you will get the information in your local air quality index. And you can also see the different pollutants concentrations as well, and the dominant pollutant, and more information. And this is the global aspect, and this is how our map looks like, and how air quality is changing with time. You can see really nicely the different roads that affect the air quality. And now the information is also available through the weather app of Apple. If you're in the US, you can go into the weather app, and air quality is provided through BreezoMeter. And there is a map also of the local air quality index by Apple. And I think this is great because it really allows us to complete our mission and to reach many, many people around the world and to increase the awareness of air quality and the effects of air quality, which is part of, it's our main mission, basically, to help people be aware and take actions. So what is our challenge? Our challenge is that, as you know, air quality is both a global phenomena. So this is a really nice example from the NASA model that shows, for example, how dust crosses the Atlantic. So we need to take that into account when we have our model, that it's a global phenomena, but also we want to be able to take into account that it's a local phenomena, for example, traffic that affects air quality. So how do we do it? I'll go over it in more details, but just kind of to give you an overview. We take data from over 50,000 monitors worldwide, so governmental monitors that are calibrated by the government. We use satellite information, we use traffic data, I'll elaborate on that. We use local fire departments in different countries. We use local sensors, I'll talk about that as well, so it's a challenge. We use different dispersion models, either models that exist as an operational models, or models that we buy, or models that we develop in-house. We use the terrain and land cover and meteorological data as part of our integration of all this. And basically what we do is we use both bottom-up and top-down approaches. So we have the measurements in real time, but we also use more statistical methods like these dispersion models. And part of the challenge that we have is how to cross-validate between all these sources of information and decide which one is the correct one for each grid point around the world, which we have a very, very dense grid of 500 meters. So this is kind of to give you an overview. I have to say that we also add a new source of information all the time. So part of my team's work is to find actually new sources of information and to integrate them if possible. And I hope actually from this talk, someone will reach out and we can also start a collaboration. We also do collaboration with different academic groups around the world. We just now in the second year of doing a collaboration with, we received a grant of the Horizon 2020, and we work with actually a group in NCAR and also with Max Planck and Finnish Meteorological Institute and CNRS and others. And we're always happy to learn and to collaborate as much as we can. So it's I call for you to ask and I'm happy to talk and to tell you more. Okay, so how do we do it? So I said before, we started, the company started when we actually collected only sounds like an easy task. It's not. To collect monitoring stations data around the world, it's very difficult. The scrapers are really, really different from, it's not the US, that it's all in very organized API. So every country is doing it differently. It's very old-fashioned collection of information. And we currently have over 50,000 monitors worldwide. But we soon realized that having only monitoring stations is just not enough. Even if you do a kind of interpolation between the stations, similar to what AirNow is doing, some kriging interpolations, it's not enough because it just doesn't answer the needs that I described before. So why is it not enough? So the first reason is validation. We have we realized that even though this information is calibrated, we see many issues of negative values, of outliers, of frozen data, of different coordinates that are in the middle of the ocean, or someone that put CO information instead of temperature, or vice versa. So the first thing that we do to all this information is we QA it. We have an automatic QA that handles all these issues. The second thing is that I mentioned it briefly before, not all monitoring stations are operating all the time. So even if I have a monitoring station, doesn't mean that it operates 100% of the time. So this is from our internal kind of system, and you can see different sensors that we have. I didn't say, but we report on 13 pollutants, not including the pollen worldwide, and not all pollutants in all countries, but we report the six main pollutants for the air quality index in all countries, which are PM2.5, PM10, SO2, NO2, CO, and ozone. So, so you can have a monitor, but it's not operational 100% of the time. That affects the quality of the information. There is also a delay in time. So I mentioned before, if I'm looking at France, different countries have different delay. There is approximately 4-hour delay in reporting the data, which is, it's a very long delay compared to air quality that is changing frequently during the day. This is an example from the AirNow website. So I actually got a question about this. You can see these two screenshots are taken in the same, almost the same time. So Monday, October 28, 2019 at 6 a.m. and here is 6:20. And we reported a fire at, let's see if I can annotate, around this region. And a customer asked me about this, why AirNow is not showing this fire. And I actually looked at the AirNow website, and it was a day after when they asked me this question, and I saw a different picture. I saw a picture that there is actually bad air quality at this location. So I asked our peers in AirNow, we work together with AirNow, and they said that they retrospectively update the data on the air quality. So the EPA, different EPAs around the world, they have a different purpose than what we have. For us, we want to report to people what's happening right now, because this is what we ask. And the EPAs around the world have more regulatory purpose. So the data is a little bit different. How do we handle this? So in addition to the fact that we combine different sources of information, at the location of the station, we use machine learning in order to predict the air quality to real time. And for that, we use meteorological data and station statistics. We do it for each station differently. So the station information and other the day of the week and the month and all this, and different parameters that affect air quality at this location. The next issue with monitoring stations is that not all stations measure all pollutants, and this is a big issue when you report on real-time air quality. So this is an example from a fire that occurred in Vancouver. You can see the smoke on our map. And in the same time, if you would have looked at the stations in Vancouver, there is actually a station at this location. So try again to annotate. If you cannot see the annotation, please tell me. So there is a station, but it doesn't measure PM10 and PM2.5, which are crucial to detect fires. So basically, if we would have just used station reading at this time, we would have reported good air quality in the time that there was smoke, and this basically doesn't help the people that we report the data to. The other thing is that even if there is a station that measures the relevant pollutant, in this case PM 2.5, the stations are far from each other, and even if they're close, they can miss the smoke plume, very easily. And this can happen either in space or time, right? Like it can happen that they detect it for 1 hour, but then they don't detect it at all. And again, if one would use only station, it would report either moderate or good air quality. Here, I show this station here in Soccer that is very close to the smoke plume, and it reports very low concentration, relatively low concentrations of PM 2.5, but it's very close to the plume. So what do? We use different dispersion models. So I said before, some of them are operational ones. I'll give one example that I can talk about actually. And some of them are models that we develop in-house. All of them are based on academic research. We don't make up anything. So we, as I said before, we rely on the giants, on the shoulders of giants. And we combine these different models. So in the case of fire, we use two different, or we buy models from the academic, different academic groups. We use two fire models, dedicated fire models, to deal with this. And the example that I said I will give is about the Copernicus atmospheric monitoring system service. So it's the CAMS. It's a great operational model. You can see it here, and it's global. But if we would have used only one model or only this model, that would also not help in answering all the needs that I described before. Why? So one example from the CAMS model is the grid resolution. I'll jump here just to show you. So this is the CAMS grid resolution. So you can see it's very different. The global CAMS is around 40 kilometers in the US. And this is how the EPA are now kriging interpolation looks like. So why is that a problem? The resolution, again, I take the same example of the smoke of the fire, of the smoke plume, and I query the information here at this location. And the CAMS did a great job in actually capturing this smoke plume, but since the grid resolution is 40 kilometers, they kind of smear it or spread it around the 40-kilometer grid. And that results in a very, very large error. So you can see here, I can, in the end, talk about it a little bit more. We have an internal tool that we check our accuracy. So what we do is we check here you can see the mean absolute error. So the difference in concentrations, in this case of PM 2.5, between what the model reported and what the station reported. So in this location, there was a station, and I compared, in retrospect, the reading of the station to the CAMS model, which is one of my input layers. And I also compared our total algorithm. And you can see that in this case, there was a very large error of the CAMS, around 380 micrograms per meter cube. The other thing that is problematic with this example of the CAMS or other single global models is that it has a delay in time. So if I take an example of fire or take an example of dust storm, you would have a 10-hour, sometimes 30-hour delay in reporting the data, which is something that people notice, believe me. So we are very, very sensitive to that. And we want to report to people right now what's going on to help them to protect themselves, to take action. And this is very challenging. So the way we deal with this is we combine different sources. So what do? I said before, we have the station data. We use it in real time. We really use the station data. So at the location of the station, you will see almost the same information as the station. We combine it with dedicated fire models that we have, but we also combine this with other sources. So basically, we use whatever we can. In this case of fires, we use also small sensors. So there is a network, or there are several networks of small sensors that are available, and we use them. And we plan to do it more in the future. We have some collaboration with different also automotive companies that have small sensors. So we will have kind of the wisdom of the crowd. But I don't have to tell you that small sensors they have many, many issues. They're sensitive to temperature changes, relative humidity. They have an issue of transforming from optical counts to mass, because the air quality index is reported in microgram per meter cube. So you need to know the density of the particle. So these are some of the problems. There are people put them in locations that are, they can put them in the garage or in other locations or next to the chimney, or we don't know what they do with them. So all of this is very, very challenging. So we developed an algorithm to deal with this. The way we do it in a nutshell is we take some of the outliers out, the ones that are not representative, and we compare this information also to other information sources that we have. So other models that we know about, and other information from other stations as well. And we use this for helping us to enhance more information in the location of the station, or in the location of the small sensors. And something we started doing right now, so this is really, really new, is user reports. So we now have many user reports, since our data is available through many of our customers. I didn't say which one, but we have a lot, and also through Apple and through Yahoo and J&J and others. So we got many people coming to our website, and we asked them to report on air quality issues. So sometimes they don't know, right? Like I gave the example of ozone. It can be a beautiful day and there is high ozone, and they see a discrepancy and they don't know why. It can happen, of course. And sometimes a report, you smell, your nose is more sensitive to something that can harm your health. But still, this information is very, very useful for us because we know where things are happening and how we can, where we need to enhance our information and use more sources of information. And we're now thinking how to actually use the user reports within our algorithm, something that we haven't done yet. So don't ask me about this. If you have ideas, I'm happy to hear. But it's something that we plan to do as well. So the other reason is that a single model is not enough, is what I said before about the local phenomena. I think traffic is a really, really good example for that. How do we deal with the issue of traffic? So we purchase data from providers, provides us traffic information in real time every 12 minutes about the location of different cars and the speed of the cars, etc. And we correlate this information to air quality at every location separately using machine learning. So we have many calculations for this feature of the traffic. So this is an example of how our data looks like. We do that for pollutants that are, of course, relevant to traffic, not for all pollutants. So how do we measure our accuracy? So first of all, we want to be able to measure our accuracy in ways that people are interested in, and we are interested in as well. So we have an internal tool, maybe I'll skip to that and go back to this, that is a continuous accuracy testing tool that has all the 50,000 monitors, government monitors that have been QA'd around the world into our system. We have all this, and we compare, as I said before, using the CAMS example, we compare each layer of our algorithm, but also the total algorithm using leave one out method. So we take each monitoring station for each pollutant out every hour, and we compare our algorithm to the reading of that station without using that station. So that gives us our accuracy between the stations and in time, because I said there is a delay also. And this we can plot in different ways. So this is an example of this internal tool. For everything together, I can choose in my internal tool, I can choose the different dates that I want to look at. I can choose the country. I can choose a different latitude, longitude of different stations that I want to look at the different parameters. And this helps me to know how to improve the accuracy in different locations around the world for different pollutants. Another metric that we plot our data is in terms of being correct in reporting the category. In the end of the day, we do this to be useful for people. And people usually, when they look at air quality, they look at it in terms of the health categories. So they care if we were correct in reporting the category. If it was good, we reported good. If it was hazardous, we reported hazardous. So this is something we do for different countries, for different regions in different air quality indexes. We report the percentage that we were correct in the category. And this is a metric that we show to different companies and also in our website in the US AQI. This I talked about. And I want to finish with an outreach activity that we do or we did. We always try to take part in different outreach activities. So this is a nice one with McCann to increase the awareness of air pollution around the world. So they put a teddy bear that is actually coughing when the air pollution increases based on our data. Share this.
Advocates have launched a unique campaign to highlight the danger of air pollution.
A coughing teddy bear
connected to a phone app called BreezoMeter.
His name is Toxic Toby.
Toxic Toby.
Toxic Toby.
Toxic Toby.
Toxic Toby.
Toxic Toby.
Are urging British lawmakers to vote on a bill.
Toxic Toby makes the invisible visible in a way that the kids can tangibly understand.
cute little teddy bear with a serious message.
Toxic Toby has made people aware just how important it is to pass the clean air bill.
So I'll finish here. And happy to take questions.
Thank you, Gabi, for the really interesting talk. Let's see if we got questions in the Slido. Not any at the moment. But yeah, well, to warm up, maybe I'm interested in asking you what have you learned in working both in academia and industry. I mean, what those two worlds could learn from each other, for example.
I think the work with on the Horizon project with the different academic groups really shows you this gap. I think we talk in different languages. I really feel that I was in the only one in the consortium that I felt is in between. So we had people from BreezoMeter, from the product, that were more UI, UX, that said, okay, the academic groups, I need the data, show me what is, how does it look like? How can I, take this information? What can I do with this? And the academic group were talking in a language of AOD and things like that are like, what is that even? And I think that this was the first time that I realized, like, wow, it's really different languages. They really don't understand each other. The scientists don't understand why the PM is asking for that. What's the problem? What they're trying to do here? And the PM, sorry, it's a product manager, not particulate matter. The product manager is asking what is AOD and what can I do with it? Who cares if you have AOD? What does it matter? And I think in science you answer questions that are interesting for you, and in the other side you try to think what's interesting for you or for society, right? But what's interesting practically, what can be, what can be done, how I can, and you start interviewing people like your family. Like, my father is asthmatic, and I try to kind of, what do you need? Tell me, I can give it to you. So yeah, I see there are more questions. So
yeah, so Gabi's asking, how do you communicate the uncertainties to the users? I assume it will be very hard to characterize the uncertainties at the high resolution that you provide.
How do we communicate uncertainties? That's Gabi.
Mm-hmm.
So first of all, Gabi is part of the Horizon project, so hi. And we usually don't communicate directly to users. We usually communicate it to companies, right? So when we talk to different companies, I didn't say it before, we are here to do good, but in order to be profitable, we sell our data to companies, not to people. So we're a B2B company. And what we do is we create different accuracy reports to these companies based on the tools that I showed you. But not only on that, we also have a confidence map that we created, and that is not only based on the live 1 hour, because we have the live 1 hour, but this is only at the location of the stations, right? And not everywhere you have stations. So we know what is the accuracy, for example, of the camps. We know what is the accuracy of other models that we use, and we combine all this together to have a number from 0 to 100 in this case, that shows what is the accuracy in every grid point. So this is information that we haven't shared with the public yet, because of different reasons. It's an internal tool, very hard to maintain, etc. But we do communicate it to different companies, and it helps us also internally.
Yeah, I imagine that the average user, if he knows that the reason uncertainty says, "Ah, this is not good," it's uncertain.
No,
It's
we have in our website a little bit of that. We have like some uncertainty in different countries, just to have a glimpse of how it looks like in the categories, but not on the grid. Yeah.
Mm-hmm. So we have Anonymous thanking you for the great talk and asking what's the most important academic quality or skill that you brought into the industry world?
Yeah, that I brought.
Maybe the one you're using the most, that, you know.
I think it's not in every company, right? So I have to say it. I think BreezoMeter is very unique in the sense that we have a science group, we have an R&D, and we have a product group. So the science group is something very, very unique. I think for the science group, the qualification that you need is really to be able to bring innovation from the scientific world. And this is something that is very difficult for the product managers to do. So product usually brings the innovation from the companies, from the trend in where I said before, let's say, the healthcare is going to personalize. So the product manager will understand that and will bring it to us and how we can incorporate it. But bringing innovation from the academic world is very difficult for a product manager, and to read papers and how to incorporate it, and also to collaborate with the different companies or different academic groups and understand what you have. It's not an easy task, and our product is very much science oriented, very much. I didn't mention the fire pollutants that we have, but we use MODIS and VIRS, and we combine, and GOES, we combine all this together, and we definitely consult with the people in the academic world for that, and I think to be able to speak in the same language is really, really important, as I said before.
Okay, thank you. Birus asking, well, complimenting you for the nice presentation, and he is asking 3 questions. If you keep retaining your machine learning model as we go forward every day, or how often you retain the model with the new data? And 2, what is your model performance for short-term severe events? And what is the forecasting window?
Okay, so I'm saying in advance that I cannot answer all these questions. So this is part of the intellectual property that we have in terms of, especially the machine learning performance. I can tell you we have a lot of calculations. So it's very, very often that we do training and learning, and we improve them. So now there is a new scientist in my group, in the science group, that is responsible specifically for improving the forecast that we have using machine learning. So we're renewing the whole thing. So hopefully we'll have a better, now we see better results. So I hope it will be seen in the data soon. Forecast, we currently provide our base is real-time data. We have some forecast if you query a specific location, but this is, as I said before, something that we are now working on to have it as an actual product and to incorporate all the layers that I mentioned before, because it's very lean, our forecast currently.
I have a very silly question.
I saw your face. I saw that you have a question. Yeah.
Why 100 countries? Where are the other 95 or so? And also, I mean, if you're doing San Marino and Vatican City and you count them as a country, is a little bit cheaty, or are those 100 countries also counting really teeny tiny countries that are embedded in a larger country? I'm thinking about Vatican City, for example. Does it have a monitoring station? I'm wondering now. But anyways, in a more serious spirit, why 100 countries? I saw that a lot of North African countries, for example, are missing, and and what's the consequence of having only these 100 countries? What would be the benefit of having more countries? Would that help your algorithm to, for example, in case of long transport events and that kind of stuff?
We take into account long transport events, right? Like otherwise we couldn't do it, but it's behind the scenes. We don't show this information. There are several reasons for not reporting data in all countries. For example, North Canada. We report in Canada, but not in North Canada, because there are not enough people that are living there. And to calculate all this, imagine our grid, okay? We have a very dense grid. The calculation is very, very expensive. So to calculate all this grid for locations that there is no use for our data is not something we can afford doing. We're not a rich company. And so it depends on the demand, basically. If there is a demand for data, we will calculate it. If there is no demand, we will not. That's one reason. And the second is the lack of information. In some places, there is just not enough information, or we don't trust the models that we have there. So it really, really depends on the location, but it's on that. And regarding the 100 countries, I don't think the Vatican is considered a country in our data, but it may be that other small places are considered. I'm not sure. Like, it's don't catch me on the 100 countries. It's more or less.
Okay, well, thank you so much, Gabi. It was really interesting. Oh, wow, more questions. Wait, hold on. Thank you for the overview of your business. Do you think the government should be addressed differently than companies, or you think that your products are relevant for both, or they have other interests?
First of all, each company, if I take the government as another use case, have different interests, really different interests. So I gave examples, but you can imagine how the data will be used differently. And yes, government have very specific interests. They're interested in long-term, for example, and climate risks. They're interested in, for example, navigating traffic within the cities. So yes, the answer is yes. We haven't yet started working directly with governments because it's tedious process to work with the government, and we're a startup, so we usually work fast. But now we started exploring this as well, because we got demand from different authorities. So stay tuned.
Very cool. Gavin says, "Hi Gabi, nice talk. I'm curious about the pollen data you present. Can you talk a bit about how you're using observations versus modeling / land use to generate them? It's being used for anything besides allergy applications? Thank you."
Okay. So this is, hi Gavin, how are you? First of all, it's a long, like I can talk another seminar only on pollen. Very briefly, we have our own model that we developed. We take into account land cover from satellite information, from inventories from the different countries. Basically, we know which tree is where in a very dense grid. Then we know the phenological factors, the seasonality of different types of vegetation. Let's say olive tree, it's different than I don't know, birch. So we calculate when the season starts and ends in a grid based on the climatology of the last year and the months before. And we know the emission, theoretical emissions from the scientific literature, but we also tune it using the weather. So relative humidity and temperature affects dramatically pollen. So this is only for the emission, kind of. So we tune our model based on the forecast, the weather forecast. And then we do dispersion to all this, and we use data, measurement data, wherever it's available to do reanalysis. It's very limited, measurement data in pollen. I can tell you in Japan, there is real-time monitoring, but it's also limited to only 2 types of trees. So they don't have the whole solution. It's an optical measurement that cannot distinguish between them. And in other locations, it's very manual. And sometimes you don't have data. The data is delayed in Italy. There are 59 stations and they're delayed in sometimes a month. So it's not data that you can use for real time. That's the shortest that I could make this answer.
Thank you, Gabi. Okay, and it's 6 minutes past 11 here in Colorado. And thank you so much, Gabi, for your talk. And thank you, everybody, for tuning in. And see you next time. I think it's in 2 weeks. Bye-bye.
Bye.